Hi, everyone. This lecture is going to be on counting. We've done a tiny bit of with this probability and looking at that denominator or that sample space, but counting, we have to be able to count up how many are in certain things to be able to find a probability. So this first one is the multiplication counting rule, or the fundamental counting principle is another thing it's called. And it's basically this idea that you times each a number of ways for each thing by each other. So like, let's think about if I had a 4-digit code to my computer where you could change your grade, right? And it was just four numbers. Then I would have 10 options for the first one. Then I'd have 10 options for the second and so forth. So those number of ways is how many for each one. And you basically times them by each other. So 10 times 10 times 10 times 10. Well, if I said none of the numbers repeat, then you would do 10 times 9 times 8 times 7. So there's like all these counting ways where we just multiply together to get the total number. And that's what this idea is. So when making random guesses for an unknown 4-digit passcode, each digit can be 0 through 9. Like we said, that's 10 numbers, right? 0 is a number, through 9, that's 10. What is the total number of different passcodes that can be made? So we just said that one out loud. Let's write it out. So there's 4 of them. So we're going to have 10 times 10 times 10 times 10, right? So 4 of them multiplied together is going to give me 10,000. So there are 10,000 different 4-digit codes with just numbers, no letters, anything else. Okay, given that all of the guesses have the same chance of being correct, what's the probability of guessing my passcode into my grade book? Well, that's a P for probability on your first try getting it correct. So I'll just call it this event that we're talking about, so I don't have to write it all the way out, but there's only one correct passcode out of the 10,000. So you can see how it's handy to be able to use like a counting principle to count up things for that denominator on a lot of ours. Now you'll use it some for a numerator as well, but the majority will be on your denominator. So factorial is an exclamation point. So highlight that for you. It looks like that, right? And so a factorial is just when you count down, we actually have a symbol for that. So this one's 6 factorial, so it's 6, 5, 4, 3, 2, 1. And like on the graphing calculator, if you go math and then over to PRB, right? Math, PRB, you can see that we do have that symbol on these, on the TIs. It's also in Desmos as well. So that's kind of helpful. So if I was to do this one with no repeating numbers, right? Then it would go 10, 9, 8, 7, right? It doesn't go all the way down to 1, so we cannot use a factorial on that one. Okay, it only goes 4 numbers out. So if we didn't repeat, it's 10 times 9, oops. 10 times 9 times 8 times 7, that's 540, or sorry, 5,040. Missed a 0. So you can see it's a lot less combinations if you don't have repeating, because you're cutting out, different combinations that you could have. All right, so be careful of the factorial goes all the way down to 1, whereas you could have a pattern that doesn't go all the way to 1. So permutations and combinations are also counting ways, but with permutations and combinations, you're like picking so many out of a total. So the top one is I'm got this many options for each thing. Whereas this bottom one is I have so many that I want to pick from. And we have 2 different ways for that same concept. We have order matters with a permutation, and a combination, order doesn't matter. Okay, so permutations are anything specific, anything detailed. So anything detailed, specific, that's where order matters. So if I'm running a race, I want to be first because I am competitive. So when you're running and you have places, order matters. It's going to be a permutation. If I'm taking I need 3 people to come represent the college at this event, just 3 people, then order doesn't matter because I just am picking 3 people. They don't have president, vice president, secretary, or anything specific. It's just picking 3 people. Culminations, another example of culminations, this would be like a committee or cards. Those are, I did not spell committee right. So those are like the 2 big ones there. Committees and cards. No, I did spell it right. It looks weird. I was thinking there was only 1 M in committee, but there's 2. Okay. And then everything else will be a permutation. So those are a little tricky. So here's the formula for those. Permutation, we say in choose R with a permutation. So we have N total and we're choosing R out. So maybe I have 1,000 people and I need to choose 3. So 1,000, choose 3. This is the formula for it, which you're welcome to use, or you can just plug it in your calculator. It doesn't matter to me, either one. I'll show both. Okay, same with combinations. We have this extra R here because we don't have as many combinations, or a little bit less. So if I had, 10 people choose 2 on permutation versus combination, the permutation would be more because we're going to divide by an extra number here. So it's going to be less combinations. Okay, so let's do some examples of these ones. So this first one says a horse race they have a trifecta bet is won by correctly selecting the horse that finishes first, second, and third, and you must select them in the correct order. The 140th run of the Kentucky Derby had a field of 19 horses. How many trifecta bets are possible? So we definitely have a permutation because it's very specific. First place, second place, third place. It's not just pick 3 horses, which there is a bet for that, but this one is specific. So we need a permutation. So this one, we have 19 total permutation, and we are choosing 3. Okay, so 19 choosing 3. So if we followed the formula, it would go N is your total, so 19 factorial over N 19 minus 3 factorial. So if we follow that, that's our formula for that. So you could kind of think of this as 19 factorial over 16 factorial, 16, 17, 19. So you could think through 19 times 18 times 17 times 16 factorial would finish off the 16 times 15 times 14 and so forth, so that you can cancel these and you really only have 19, 18, 17 being multiplied. So there's a total of 5,814. All right, so that's one way to think through that. You could put it in the calculator with the factorial button. You could also do 19 choose 3, which I'm going to show in the split view. This is like a fake graphing calculator. So if we'd go to math, and then we go over to PRB, and you can see 2 things there. You can see the factorial and also the permutations and combinations. Okay. Oops, but I forgot something. I think it'll let me do this. Yeah, it will. Okay, perfect. On this calculator, you might have to click the 19 first, then go in and hit that button on the older versions of the calculator. And then I need to go there, and I have 19, choose 3, enter, and it should give you the answer. So usually you have to hit 19 first, which I think I could show, and then do the PRB and then permutation. Nope, this one does it different. Okay, but anyway, make sure you figure out how your calculator does that. Okay, so formula or not, another way that you could have done this one, it only works for permutations. Your logic could have gone with, I have, oops, there we go. I have 19 choices for the first spot, first place. Whoever got first place, then I have 18 for the next and 17 for the next. You could have just thought through this and not done a permutation at all, and you still get the right answer. So with order mattering, you can think through the multiplication principle. So when you start a problem, it just depends on how you think of it. Now, combinations, you don't have a choice. You have to use a combination because then you would have to divide by however many you're choosing from. I don't think that's as easy to think of. So part B, a better, a better, meaning someone who's betting, randomly selects 3 of the horses for the trifecta. What is the probability of winning if we ignore dead heats, which horses tie or win? So what's the probability of winning? It's just going to be one chance out of, oops, change that back to black, 5,814. Okay, which is super small, 0.000172. So what's the probability of winning a trifecta at a Kentucky Derby? Very minimal, which means if you win it, you win a lot of money. Okay, number 2. In California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order doesn't make a difference. So order does not make a difference on this one. And this is common Powerball, how it works. So for the first one, how many lottery tickets are possible? So we are picking only one of the 39, 5 of the 39. So we know it's going to be 39, choose 5. Okay. And if we used the formula for this one, we know it would be 39 factorial over 39 minus 5 factorial times r factorial, that extra 5 factorial on there. So if we did this one out, it's a little bit harder to do because it doesn't cancel quite as pretty. But the bottom one would be, so I have 39 factorial over, well, I don't know, let's see. So that's 34 factorial, 5 factorial. So to do it by hand, you can count out the 39 and then you have to divide it by the 5 factorial. So that's a little bit harder. So I could just put in my calculator 39, go over to the factorial button and divide that by 34 factorial times 5 factorial. It's kind of a pain to do it in factorials. And I got a big old number. So I got 575,757. So the other way, right, is to hit 39, go into PRB combination 5, and you should get that same number. That's how many are possible. Now if you were doing, I'm going to pause and go on a tangent, but that's okay. If you were doing the real Powerball, you have those 5 numbers, but you also have that red Powerball. And so you have like one other number. And so you have to times this answer we just got by like 39. Because you have 39 more choices for the other one. So it's like so many choices for the first ball, and then the first 5 balls, and then one other choice for that last ball. So it's a little harder if you're doing a real Powerball. I think you have one in your homework. And the probability, if you get one ticket, you have one chance out of all these chances, because that's as many tickets as they can sell, because that's as many combinations there is. Actually, I guess that's not true because you could share the jackpot. Well, that would bite. You finally win and you have to share. Okay. So anytime you're given a whole number like that, then you're going to have to think through, you have a combination, and you're going to have to do um, uh, a combination. You're going to have to do the combination. I can't even think of the word permutation all of a sudden. You have to use the C, right? You cannot do it any other way. Okay, so the other way, I don't know, 38, 37, oops, times 36 times 35, and then divide that by 3 times 2 times 1, right? Oops, 5. Okay. I was going to show this other way, but I wanted to make sure I just wasn't thinking quite right on that one. Yeah. The other way that you could think through this on your own is you have 39 choices. So this is just another thought, right? For the first number, then 38, then 37, 36, then 35, 1, 2, 3, 4, 5, but you have to divide it by 5 factorial. So that's what I meant by like a permutation. You just multiply them across, but that combination, you would have to divide by 5 factorial, or because that's the numbers that you're leaving off each time. You left off 1, then 2, then 3, then 4, then 5. So that's where that comes from. So this gives us the same answer here. So trying to get you to think through probability is hard. All of us think through it a little bit different. So question 3, I have a 6-digit code to my gradebook with 1 of 4 numbers allowed. Repetition of digits is allowed. And then what's the probability of guessing that on the first time? So this is a 6-digit, but you only have numbers 1 through 4. So that's 1, 2, 3, 4. That's 4 digits. So all 6 of them, I have 4 choices for. So you can think of it this way or this way, right? Either one that you can think of. And so that's 4,096. Okay, so there's 4,096. What's the probability of guessing that, of this event here? Is just 1 out of that. Okay, if there's only 1 correct answer. If you bought more than 1 ticket on the one above, then the top number would not be 1. It'd be however many tickets. But okay, if a presidential candidate, he plans to visit capitals of 4 out of 50 states, what's the probability she selected the route of 4 specific capitals? So if I'm looking at this presidential plans, I have 50 states, I'm only going to visit 4. Is that going to be a combination or a permutation? It says specific capitals. You don't want to go to the same one over and over and over, right? So you want it to be unique. You don't want repeating. So this one doesn't say it's specific, but you have to think like, I don't want to repeat. I want to go to 4 different ones, is how they worded it. So that means I have 50 choices for the first one, and then 49 and so forth. Or you could think of this as 50, choose 4, and it is a permutation. So I'm going to go 50 into my calculator. I'm going to do a permutation 4, and I got a big old number. 5,527,200 ways for you to go to 4 capitals. So if you would have thought through it this way, that was totally fine as well, right? That gives us that same number. I don't need to divide because this is a permutation, and the probability of selecting one specific route, right? That specific route is going to be 1 out of our 5,527,200. Not very likely. If you round that probability, it's going to be a 0. Okay, question 5. There are 25 students in class. I need to pick 3 people from the class. What is the probability of picking a team? So we're picking a team of 3 people. That's not worded the best, but with this one, we we don't have a specific order. We just need three, like a committee, a group of people. So it's a combination. So 25, choose three. It's a combination. So we can just do that straightforward. You can follow the formula, or you could do 25, 24, 23, but you have to divide it by 3 factorial, or 3, 2, 1. Okay. Any way that you think about it. So 25, I'm lazy. I'm just going to put it in this calculator right here. I get 2,300 ways. So in my class of 25, there is still 2,300 ways to pick a committee. And those are lower than a permutation. So lots of ways. Okay, this problem has a little bit different formula. So how many ways can the letters in Mississippi be arranged? Well, think. There's so many S's and I's and P's. I can't tell the difference between one I and another I. So when we have repeating, we're going to have the formula. I thought it was at the top. Do I not have it? Yeah. Here is a permutation rule. If there are some identical ones, it looks like this. So let's see what that looks like in terms of a problem. So what we do is we look at how many letters are in Mississippi. So 1, 2, 3, 4, 5, 6, 7, 10. So I have 11 factorial on the top because that's our total letters. And then on the bottom, you need to divide out the ones that are repetitive because I can't do 11 factorial because I can't distinguish between every single letter here. So there are 1, 2, 3, 4 I's. So I'm going to do 4 factorial for the I's. I don't know why I made that look like a fancy I there. And then there are 4 S's. So that's for the S's. And I see 2 P's. And then I don't see any other repeating. So then we'll calculate this out. And you still have a ton of numbers here. 34,650 according to my notes. So if something's repetitive where you can't tell the difference, you have to divide by it. Okay. If Mississippi had all unique letters, I could range it in 11 factorial ways because you'd have 11 ways for the first one, 10, 9, 8, 7, 6, 5, 4, all the way to 1. So you could count all the way down if you're using all of them. Or like 5 people are running a race. How many ways can they get first, second, third, fourth, fifth? It would be 5, 4, 3, 2, 1. You multiply all the way down because you had all of them. Well, let's think about an area code. How many people can use, let's just use our Wyoming area code. How many people can use 307? Well, then we have 3 spots, right? And then 4 spots for a phone number. So we have 7, right? 4, 5, 6, 7 more codes here. How many numbers can I use for each spot? I can use 10. So this is leaving 10 to the 7th more numbers, or, 10 million. Whooshka, booshka. Right? 1, 2, 3, 4, 5, 6, 7. So you need 7 zeros for a 7 power. So yeah, 10 million people in Wyoming before we run out of 307 area code. I don't think we're going to get there, y'all. I'm pretty sure we're safe. Okay, so a lot of the questions can get a little bit harder. Like this question we're on right here, it could say no zeros are allowed in that first place. If you don't know why we don't allow 0 here, it's because you're not as old as dirt like me, where if you click 0, you used to get a person, like an operator. So you couldn't have your number start with 0 because you're going to get the operator, which doesn't exist anymore. So if you had this one off, then you'd only have 9 choices for this number, 10, 10, 10, 10, 10, 10. So you could do any other kind of pattern if needed. Okay. All right. That's all I got for this lesson.